Hey, all right, everyone. It's 2 o'clock, so we're going to get started. I'm going to give an introduction to Kenny Daniel. He's been in academics with AI. He's been a practitioner in industry, and most recently, he's founded Algorithmia. He studied AI in Carnegie Mellon and Southern California, and today he's going to give a talk on some of the DevOps issues with ML. If you have any questions, post them in the chat, and just like David mentioned, put a Q colon at the start of them, and Kenny can get to them at the end of the chat. Without further ado, here's Kenny.
Great. Hi, everybody. Thanks, Patrick, for the introduction. As he said, going to talk about DevOps and how it applies to the world of machine learning based on my years of experience in the field. So the introduction out of the way, we can just dive right into it. So just to start with, and to kind of get everybody on the same page, I want you to think, if you're starting a project, it could be any project. It could be just a side project for fun. It could be a new project at an enterprise, or founding a startup that's going to have some component of ML that you're going to want to deploy. And the question I want you to think is, how would I actually go about deploying this model? And there's a number of ways that you can approach this, and different approaches, things that have different pros and cons. But what I think I'm going to argue, especially in this talk, is that we need to figure this out as an industry, and figure out what are the best practices, what are the procedures for doing this. So the big thing, this is something that I think is critical to our industry. I've been in this industry for a while now, and lived through the AI winter, so to speak. And in my opinion, the reason that happened to a large extent was that there was a lot of interest and excitement around AI and machine learning, but people failed to get return on investment. Companies invested in it. A lot of companies are investing now, and if you don't get success with these projects, if you don't deliver return on investments, enable things that couldn't have been done without machine learning, or save huge amounts of money by automating things, if we don't achieve those things as an industry, I think there's an existential risk of funding decreasing and setting back progress. And I think we're all here and wanting the same thing of more and better tools and technology. So that's why I really want to emphasize that, just doing machine learning is not the same thing as doing machine learning in production. And there's a whole bunch of things that go into why that's not the same thing. So probably don't need to tell anybody at this conference this, but, DevOps broadly, I like to think of it as a set of practices intended to reduce the time from wanting to make a change to actually getting that in production in the hands of your customers and your users. And we have over a decade or 2 decades or however long of applying DevOps to traditional software, but this is very new concept in the world of machine learning. So I'm very excited to have conferences like this one, talking about sort of the challenges that go into that. So again, broadly, the theme of the talk is drawing an analogy between traditional software development lifecycle and machine learning, because there's a lot to learn. And if there's an unspoken subtitle of this talk, it's, why does machine learning industry suck at DevOps, frankly? If you were to go start a company or start a project in building a web app or a traditional sort of software project, and you said, nah, I think all this source control management stuff, CI/CD, testing, observability, all these things. If you just said, I don't need those, that seems overhyped. I'm just going to go it alone. I'm just going to, commit straight to master. I'm going to, do all these things and ignore all these best practices. Frankly, you'd be laughed out of the room. There's a reason why these things are best practices. It doesn't mean you implement them all at once, but like if you weren't working towards that, you wouldn't be setting yourself up for success. And so in all of my time in the world of machine learning, in academia, never once mentioned source control. Even still today, we see Fortune 500 companies out there that have teams of data scientists that aren't even source controlling their training code or their code for inference. And that seems crazy, frankly. And a lot of the tooling is not really set up super well for that. As for example, Jupyter and things like that. So let's dive a little bit deeper into the sort of this idea. And so the software development lifecycle, for those not familiar, there's a number of possible definitions and things that this encompasses. But broadly speaking, it's the things that are table stakes for software development. Control management, clear winner in that regard. CI/CD, everybody's got their favorite tool of choice of Jenkins or GitLab or Hub Actions or whatever it is. But again, this is ubiquitous. This is in every company these days. How do you automate the deployment? It shouldn't be a person at a keyboard sitting there, manually uploading things or running commands. That's it doesn't fit with compliance, but it's also just not good for developers or for the company, and it inhibits moving quickly. And so, having solutions for that is going to be really key. And similarly, and especially now, like this is in the world of DevOps, the really big thing is, how do you get observability? How do you get insight and introspection into the running system so that you can diagnose things and debug things and understand what's going on with your live systems? So I would argue that, we need to be asking ourselves as an industry, what are the analogies for those things in the machine learning world? Some of them translate pretty directly. As I was saying, I'm definitely an advocate of source controlling and checking in your code for both training and for inference. But for CI/CD, there's kind of some unique requirements in these worlds, and we'll dive into this more in the rest of the talk. But that's what I want to kind of start getting everybody thinking is, what are the analogy of tests and continuous distribution and integration in the world of machine learning, and how can we level up as an industry on those tools? So there are differences. Machine learning has fundamentally different characteristics in some ways to traditional workloads, some of which are compute related, others are just in terms of this life cycle. And agile development and software development, it's all about building feedback loops. And you push code, you test it, you see how it runs, and then you go back and you iterate it and you update it next week or the next day. Machine learning is similar, but there's an extra step in a certain sense, because there's the training phase, which is distinct from the actual sort of inference phase. But you do want feedback loops through this whole thing. There's also the aspect that the output of a machine learning model does not depend just on the code you write. It depends on the model and the weights and then the output of the training. And so that's another consideration, where even if your code hasn't changed at all, it's the same Git hash. If the model changes out from underneath it, that's going to have a different output. And so any pipelines and life cycles that you build have to be aware of this and build that into the understanding. So this is a concept that I really like, is just, and this is core to DevOps really, is speed of iteration is everything. And this was not invented by agile software developers, or it wasn't even invented in the last couple decades. This was observed, even back in the 1950s, in the context of dogfighting aircraft, and this was Boyd was a general and who was studying sort of academically how to be more effective at aerial fighting, and he realized that basically the speed of iteration beats quality of iteration every time. And so if you can adapt and improvise more quickly than anyone else, that's really going to be key to success, even if each individual step is not as good. This is pretty widely accepted in sports and software engineering. This is not controversial these days, but achieving that has got to be key to machine learning success. So I want to dive a little bit deeper into kind of each of what I'll call the 4 stages of machine learning lifecycle here. The first stage is the data. Everybody knows that. There's going to be plenty of talks in this conference about that. I'm actually going to mostly not talk about this at all, just because it is such a deep topic and I want to talk about the later stages. But there is lots to be said about data. The quote putting here is that, for decades, really, people have built acquiring data, accumulating data through big data, data lakes, all these things. But again, going back to the original point, if you don't get return on investment on that data, then there's going to be backlash, and it's not going to be good for anybody, really. People spent millions and millions of dollars accumulating this data, and what they're realizing now is that if you don't have machine learning and algorithms to make sense of that data, then piling up all that data is useless. But similarly, machine learning algorithm is not any good on its own. It needs to be paired with data. It needs to be paired with the right use case, and it needs to be able to access that and take that into consideration. So there's a lot to be said there, but I'm going to gloss over that for this talk. So training. So training is a phase that doesn't even exist in the traditional software engineering lifecycle. So it's worth addressing a little bit. And characteristically, training is obviously very different than the deployment and running and inference. It's a very long compute cycle. It's exploratory. The training is very often done on somebody's laptop running Jupyter Notebook. It's an interactive REPL type environment. You want to be experimenting with features. You want to be iterating and doing it quickly, and having a fast feedback loop there is absolutely critical. I talk a little bit, it's not a perfect analogy, but it's very stateful in a certain sense, that even if you're training across a distributed compute cluster, there's still sort of a central job being run that's being orchestrated, and you can parallelize things, but like in a certain sense it's a one-off, or it may be run for hours or days or weeks at once or a couple times, but then there's a distinct transition from that training phase into production, which is characterized by, in many cases, it depends on the use case, but being almost completely stateless when you're actually doing the inference. You take an input and you output a classification, or whatever the category of ML problem is. But you can parallel. It's embarrassingly parallel is the technical term for it, right? You can just copy it, replicate it horizontally, and handle as many results as you want that way. In contrast to training. It's going to be bursty. You can't necessarily predict the usage patterns on inference. Training, like I said, it's going to be once or a couple of times off. It's going to be very heavy. Running and inference and production, that could be following Monday through Friday 9 to 5. There might be monthly or nightly batch updates that have a really huge spike in traffic. So these are very different characteristics that are considered when you might want to choose the best tool for each job. And the more important and bigger and more valuable a project is, the more you want to find the best tool for the job. So how do we bridge that gap between training and production? So as I was saying earlier, first of all, source control and Git is not even as ubiquitous as I think it should be in our industry. But in the place where it is, there's also this issue where the code that runs the training is different than the code that hosts it. So there's a question of how do you manage those two distinct phases. And one of the things I'm a big fan of personally is what I call the 2-Git flow system. This is kind of drawing an analogy. There's things called like Git flow, which is just best practices for how do you work with Git, what do you name your branches, how do you merge things in and collaborate with other people. So I would argue we should, and this may not be the way, but we should be talking as an industry, how do we manage this? Is there a training repo that's distinct from the inference repo? I would argue yes, because they operate under different life cycles. But there's other ways you can do it, having different directories within the same repo, things like that. But it's absolutely something that I don't see talked about enough, in my opinion. So how do you then go from training? So say I'm working in Jupyter Notebook, it's interactive. Jupyter is not a hosting solution. It's just not. I mean, it's interactive. It's an environment, really. It goes a bit beyond that, but at its core, it's meant for that interactive sort of exploratory phase. So there's a couple ways that you can go seamlessly from there, and I'm definitely an advocate of having this be as automated as possible. So one thing that I've seen that's really effective is let your data scientists work in Jupyter Notebooks that they want to be working in. Check them into source control. And you can, with pretty minimal boilerplate code or with configuration of your CI system, depending on what that system is, you can make it so that when a data scientist pushes up a notebook that they've trained on, you can very easily have it execute that notebook in a container, and with minimal sort of boilerplate at the end or through configuration of CI, have it train the model on a cloud potentially, like as a result of a CI event, and then when it's done, push the model up to a hosting platform. This can be overkill in some cases, but I would argue that it's a lot better than the situation of, oh, I trained a model on my laptop. I'm going to take this pickled model file, I'm going to manually drag it up to S3, and then configure a web app to use that. The problems with that, and especially if you get into industries that are more regulated, or even just more valuable use cases, you need compliance. You need to ensure that one person can't single-handedly manipulate that model, or even just make a careless oversight. That's why we need sort of these tools and these best practices, is in order to prevent that human element from causing problems there. So ML deployment also has some unique challenges. You might ask the question, well, if we've spent 1-2 decades of building all these tools and solutions for deploying software and web applications and services, why not just use them? Well, the sort of obvious one, or at least one of the biggest issues there, is that there's pretty unique hardware requirements. For example, GPUs. This is not universally the case, but for a pretty large amount of machine learning workloads, especially anything that's going to be deep neural network related, of course, you frankly need specialized hardware in order to be competitive. And sometimes it's GPUs, it might be TPUs or other ASICs that are coming out and all that. But fundamentally, there's a question of how do you do that? And if you're, for example, you might say, hey, I already have a Kubernetes cluster that's running, for my web services and my web apps. We have a whole team dedicated to maintaining and running that. Why can't I just do it there? Well, you can, but there's questions of, do I put a GPU on all of my machines there? How do I start segregating this to make sure that the workloads are going where I want to go? And furthermore, containerization is something I haven't talked about too much, but it's very front and center in the minds of people. And again, with DevOps, that's pretty standard these days. If you're not containerizing your traditional workloads, it's going to be very difficult to work with them, broadly speaking. With machine learning, it's doubly difficult in that regard. So what I'm kind of showing here is, if you have 2 Docker containers running on the same machine, it's not completely 2 isolated things the way it is if those were running in 2 separate VMs. When you're running 2 things in Docker containers on the same machine, they share the same kernel. And anything that lives in that kernel space is not going to be cleanly segregated using Docker and using C groups. And what lives in the kernel? Well, for relevant to us, most importantly, is going to be things like GPU drivers and hardware drivers and CUDA and all that. And so suddenly, it's not just what you put in your Docker container, it's also what lives in the host VM that's underlying this. And so it's not enough to just use an off-the-shelf container or Kubernetes system. You now need to be doing things like bind mounting in the NVIDIA Docker sockets in order to make it so that your containerized workloads can even make use of the hardware. And then furthermore, there's the question of, okay, great, even if you do those things, how do you prevent them from workload 1 from stepping on workload 2? And the fact of the matter is that GPUs don't have the kind of memory protections and boundaries and security boundaries that system memory does. Things are starting to get better in that world, but fundamentally, GPUs were made to make video games fast, not to run enterprise production workloads in multi-tenant environments. Oh, clicker's not clicking. Again, going kind of into the unique challenges that ML presents for deployment, there's pretty heavy framework. So even if you get the CUDA and the CUDA and the drivers and all that worked out, TensorFlow, PyTorch, all these things are in many cases multi-gigabyte affairs. And so there's a question of, how do you efficiently deploy those and make sure that everything works nicely together? And sometimes you can just do that with a pip install, but in other cases, it's not that simple. And there's also, if you want to deploy a lot of these things, if every one of them creates a new Docker container baked from scratch, each one of those is going to be really large. And if you're not careful about how you construct those, they're not going to have shared common layers. And so suddenly you need to spend a lot more time and a lot more disk space downloading and loading and extracting and all these containerized models. And if you do that, it's going to reduce your efficiency, your utilization of your hardware, and it's also going to affect your scaling, because if it takes a long time to spin up another replica because you have to spend 2 minutes downloading a Docker container, you need more overhead in that world. Because if you can spin up really fast, you don't need as much slack overhead when you have unpredictable workloads, because if you can spin up in seconds, then you can just respond to demand dynamically. But if you know that it's going to take 2 minutes, 3 minutes, 4 minutes, whatever, to load up a new replica, you need to have more slack capacity if you don't want to be dropping requests or failing to keep up with demand. So that's really critical, is being efficient with how you design your base layers and deploy them out to your worker machines. And this gets even more complicated as you get into the world of things like natural language processing, where you're often going to be pipelining lots of different components together. First step might be, converting a PDF to text so that we can even start to work on it. But even from there, you need to know what language it is. You probably want to vectorize the text and, do all of these transformations. And so being able to combine them and make sure that, when you have multiple containers that want to, send data from one to the other, that is your scheduling system, making sure that those run near each other. And things like that can make a huge impact on the performance, the overhead, and the throughput of your machine learning system. So, okay, after you deploy it, what then? Well, there's management. And in many cases, a lot of companies haven't even gotten to this stage of machine learning maturity, but it's absolutely something that's looming on the horizon. And there's a number of things that go into that. And again, if you look at a modern, DevOps or infrastructure department in a company, they're working on a whole bunch of things. They're working on testing, but we'll go into that in a minute. But there's multiple kinds of testing that you want to do it. There's the getting insight into the system and all that. So these are things which may often be forgotten in the early stages, where the only goal is just, hey, I have this model, I need to get it available as an API or as part of our backend pipeline, so that we can actually start getting results and getting return on investment. But pretty quickly, what will happen, as soon as you want to update that model, or add a second model, or retrain on a nightly basis, or just update based on new data, is you'll have these questions of, how do I manage that going forward? So there's things like testing. This is on this slide kind of what machine learning practitioners often think of as testing and evaluation, is these sort of, metrics and things that is computed during training and often guides the training. But I would argue there's actually more to it than that, and there's more nuance to what is a test. And so this is a kind of a drum that I like to beat, is, if you look at testing on traditional software, there's all sorts of interesting things. It's not just top of line pass fail or top of line, percent accuracy. There's things like unit tests. And so why aren't there unit tests in the machine learning world? Because it might not be that I just want 90% accuracy on my whole data set. I also want to make sure that for subsets of that data set, maybe it's a subpopulation of my group, or just, particular parts of the data that have a different input distribution. How do you ensure that those continue to perform well as you update the model and as the data evolves? So I think that there's absolutely room for things like that, of, running unit tests against machine learning to make sure that things like that, integration tests, smoke tests, performance tests, and stress tests. How do you know that? What is the throughput? How can you ensure that it's going to be able to handle X many requests per second? Are you filling the pipeline of your GPU, or are you passing just one inference in each time and massively underutilizing your GPU in that case? There's a lot of things that go into that. And again, don't have time in this talk to go into all of them, but I think that just asking ourselves, hey, what are some of these lessons that have been learned in traditional software, and how can we make machine learning better? I think there's a lot of opportunities there. Auditability and governance, again, thinking how do you get insight out of this? Are your models emitting meaningful metrics in addition to, the answer that they're outputting? And can you access those in a systematic way? There's, model drift. So even if you don't, well, there's data drift and there's model drift and there's other kinds of drift and all that. But, just kind of visual example, maybe you trained your model in the summer. This was kind of a real example we did as a demo. We worked with a clothing company on a fashion detector algorithm. And, so we took a bunch of their data, we trained up a classifier on it to recognize things like shirts and pants, et cetera. But then you wait a couple months and it goes from summer to winter. And all of a sudden that classifier that had, 90 whatever % accuracy no longer works because the data has fundamentally changed, even if you haven't made a single new commit or changed anything in your model. And so that's something that's a little bit different than traditional software, where if I do a git push and I change the code and I run the tests, those tests are probably going to just keep passing forever into the future because nothing changes. But with machine learning, your input distribution might change, your model might drift. There's all sorts of things in that regard. And then, there's also a lot of thought leadership going now in the DevOps space of, what's the best practices around logging for web applications? How do I do monitoring? How do I get alerted when things are going wrong? And observability is even deeper of, how can I answer questions after the fact about, why things happen the way that they did. This also starts to touch on explainability in machine learning, but I think it's also distinct. So that was drawing some analogy to between traditional software. What are some of the differences with that and machine learning, and how do I think about this sort of problem? Machine learning is a very new space, and so being able to draw analogy is really powerful in that. So why is it that what's the source of some of these problems? Like, why is machine learning behind the curve when it comes to DevOps and these sort of best practices? Well, I would argue that there's a couple things that go into it, and we'll dive more deeply into each of these. Sorry, slide a little out forward. So what are kind of some of the things that we see firsthand as the things that, we work with a lot of customers. We talk with a lot of enterprises that are working to build their ML strategy and their tooling and their infrastructure and figure out how they can make that effective for them. And so we see a lot of anti-patterns, which tend to come up. One of them, stuck in the lab. So a company will invest in hiring some data scientists, some ML engineers. They'll potentially build things like innovation centers and things like that to try to pursue this, because they recognize that there's value in ML. But this can often be a trap where it's easy to have people, playing with data, building models, things like that. But if you don't have the right alignment and connections in with the rest of the company, it's very easy for those projects not to go anywhere. And that's why we talk to a lot of companies, and there's data out there and surveys of, a lot of companies haven't even gotten their first model into production. And that can often be a sort of a symptom of this, where it's, they might have data scientists, they might be building models, but if they're not actually getting into production, that means that it's getting stuck in the lab, and that's a big problem. Oftentimes that can happen because the right people are not talking to each other. Sometimes that's asking data scientists to build infrastructure. And fundamentally, it's a very different problem. They're both interesting and require expertise. But, if I spend, 10 years of my life learning to be the best DevOps engineer that I can, or I spend, decades learning to be the best ML engineer and learning all the art and the science and the math behind, deep learning and regression and all these things, that's not the same skill set as building a reliable, scalable system. And so asking those people to do them can often be a recipe for problems. additionally, not talking to the business owners, the users or product owners. Again, if you don't want to get stuck in the lab, you need to make sure that it's going to have an impact on the product. And again, this is, in my mind, this is existential for our industry, is making sure that we do get out of the lab and have an impact on the business. And understanding who's responsible for these things. Different organizations have different structures, and there's not a right or wrong one, frankly, but understanding those, having a process and understanding who's responsible, because if you don't know who's responsible for what, then there's this abdication of responsibility, where, maybe a data scientist doesn't want to go build a Kubernetes cluster in order to deploy their work. Or, there's question of who owns the budget for that, and how do you get authorization to actually pay for things? Because it's pretty easy to do a lot of the first stages of data science on a laptop with free open source software. But as soon as you need to go host and produce it, there's definitely going to be infrastructure. And frankly, there's probably going to be software costs too, if you want to have the best solution for your problem. And fundamentally, there's also a lot of technology questions of just, how do you choose the best technology for this? And it's a very fast evolving industry. So even just the frameworks from a couple of years ago, when it was all TensorFlow, nowadays PyTorch probably arguably has the majority of the mind share. It's certainly in the research side of things, and community sentiment. And so who's to say what that's going to be 1 year, 2 years, 3 years from now? And that even just that decision, that cognitive overhead can be inhibiting to adoption. So I think maintaining some flexibility, because you don't want to tie the hands of your data scientists and your engineers, but you do need to have some opinions, and you do need to make those decisions and keep moving forward, even if they're not perfect. You don't want the perfect to be the enemy of the good. Stakeholder buy-in, kind of mentioned that already. And then just broadly speaking, lack of process. A lot of times it's just, you ask somebody, hey, what is your process for going from a model that was trained by a data scientist in your organization to, hooking that in and getting that up? A lot of people just don't even have an answer for that. And, that's something that, again, with traditional software companies have to figure out as they mature and as an organization. And I would argue that, you need to put that same thought and deliberateness into it. And that's kind of what this whole conference is about. So I'm really encouraged to see that. Broadly speaking, ML is in a huge growth phase. It's very exciting. I love how excited the world is and the investment into that. But again, it's lagging behind on some of the sort of the practical realities of this. And so that's where, I think as an industry, there's a lot of opportunity for improvement there. And again, it's just, we want this to be successful. Like, this is, the closest crocodile to the canoe. This is going to be the thing that sinks us in a certain sense if we don't deal with it immediately as an industry. Running a little bit low on time, but I will say that, again, going back to the idea of it being a trap and there being hidden technical debt, it's not necessarily hard to get your first model up in production. Make a VM image, make an AMI, add it to an auto scaling group, you're off to the races. One person can do that in an afternoon. But what happens when you have your next model? Do you create a new auto scaling group and do a rolling deploy? What happens if you want to call back a couple versions and see what those are going to do? What happens when you want to add your second model and now there's no consistency between them, or you do add your second model but you didn't update the scripts for the first one? These are sort of the hidden technical debt that can catch up on you. Google wrote a really good paper on this about hidden technical debt specifically. And so finally, kind of take-home points, considerations for ML in the enterprise. And by enterprise, I just mean in business, getting return on investment, proving the value in these tools that we all love and believe in so much. And so, one, the biggest thing I would probably say, don't reinvent the wheel. This tweet kind of sums it up pretty well, in my opinion. Like, we talk to a lot of companies and there's a lot of teams in there that are just a bit too excited about building their own solution for this. And, I get it, like, it's interesting problem space and there's a lot that goes into it, but it's really easy to think that it's going to be easier than it is, or forget about some of these nuance that's going to come in later. And, you're going to either be on the hook for building, or, you're going to have to figure out, what you're going to do instead. So, again, if there's one takeaway from this talk, it's that doing machine learning is not the same thing as doing production machine learning that's having an impact on business and the world. And we've spent 2+ decades learning these best practices the hard way in software engineering and in DevOps, and there's conferences and talks all around the world going about these things. And I think that we as an industry could really benefit to like open our eyes, look at some of those things and ask ourselves, yes, it's a new industry and it's greenfield and like nobody knows where it's going, but that doesn't mean we don't have a map. We can look at traditional software and see, let's take the best parts of that, forget the parts that don't make sense. But, I think that there's a lot of room for improvement for us as an industry. So pick the right tools for the job and, make ML successful. So that's what I got. Thank you. There's some further reading here. Ian Chow, I think, really like nails the sort of issue of the existential risk to machine learning. And as I said, Google has some really good talks about the hidden technical debt, and the roadmap to machine learning maturity has some good data backing up the things I'm saying. So thanks, everyone.
Yeah, thanks, Kenny. That was a great talk. So there's a lot of interest in the chat as well. You can see there's some of these questions in there, so feel free to jump through that. There's another talk coming up in about a minute, but everyone can feel free to stay on and continue the discussion.
Yeah, absolutely. I'll start reading through those. And yeah, sorry I ran a little long there. I'll be still on the video though, so I'll try to get through all the questions if people want to stick around. Or feel free to just email info@Algorithmia or Kenny at Algorithmia. Happy to address anything there. I'll start reading through some of the questions now. To the people asking about the deck, yes, the deck will be made available. I was making last minute edits up till last night, but I'll absolutely make that available. And again, just email if anybody can't find that. It's all open information, so happy to share that. Some people talking about some of the different tools and services, ECS, Fargate, etc. So yeah, again, there's a lot of tools and things out there that are great. They're in many cases not machine learning specific, and that can lead to some challenges. But absolutely, by all means, check out those tools and use what you can off the shelf. Got it. Okay, so there's a really good question here about what do you think of using standard code.py files instead of IPython notebooks for training a model? This way the team can collaborate, but it's not that convenient for a data scientist. So I think it can work different, at different organizations can do it differently. I actually think that for the training phase, it does make a ton of sense to stay in an IPython notebook, a Jupyter notebook, because it is often interactive. It's exploratory, and you want to be able to go back and change one step without having to rerun the whole notebook start to finish. With software development, there's pretty widely accepted thing, which is that the shorter you can make that feedback loop, the more effective a developer is. If I have to push to Git and then wait for a CI job to complete over 10 minutes and all that before I get feedback of whether my code change was good or not, that's going to make me much, much less productive as a developer than if I can just, run tests locally and iterate that way. So I think there's an analogy there with a Jupyter notebook. And you can run a Jupyter notebook like a Python notebook. I forget the exact command line, but you can basically just treat it as a Python file in a certain sense. So I think you can run that on the back end that way as well. There's a subtle nuance there where, if you're doing nightly retraining jobs, that might not be a situation to run in a Jupyter notebook, but, again, it kind of depends on the situation. Cool. Let's see, scrolling down. Best model version control technology you've experienced. I'm just going to selfishly say Algorithmia. We keep every version of every model. We actually link it to the Git source repository, where if you do a Git push, we build that model and we tag it by the Git hash. So you can call the API directly based on the Git hash, and going back in any version in history. And so that I think that there's some niceness there, but I'm not unbiased. Let's see, sort of final question. Any way to get the IPython more development friendly and examples? Yeah, again, I think just thinking about it where, even if you do it interactively as you're doing it, making it so that at the end of the day, you can just run your notebook from start to finish, and that the output of that notebook is going to be your trained model file. I think that's a really good best practice for building your notebooks, rather than assuming that it'll be a person going through and like looking at it. So yeah, I think there's absolutely best practices there, but it wasn't the focus of Jupyter Notebook, right? Like, they're focused on that interactive thing. And so I think that they're getting better, but there's a lot of room for improvement there. Thanks for the question. And yeah, people talking about Jupyter plugins and all that, which, there's probably people much more expert than me on that. And then so the question, final question, I guess, about the 2-Git flow system. So again, this is just something that I've kind of proposed, and I've started to see some of it in the industry, but it's just recognizing the fact that, you have 2 distinct code bases. There's one for training, and the code for actually running the inference is different. And so having a separate Git repo, I think there's a certain analogy to, like, the migration towards microservices and not having a giant mono repo and having things tracked distinctly. Look, there's certainly pros and cons of different approaches. I don't think there's a right or wrong one, but asking that question and having an opinion about that, I think it can go a long way. Because again, it's not what system, using the Git flow system versus other, Git management systems. Like, I don't think that it's right or wrong to choose one or the other. It's just have something, have an opinion, have something, and that's really key. Cool. Let's see. Any other questions? Doesn't sound like single flow can work for all deployment types. Sorry, Heathcliff Lewis. Could you maybe give a little bit more detail what you mean by that? Batch type workflows. Yeah, so that's often a big question is, batch workflow or real-time type workflows. And, look, I don't want to overgeneralize, because there's a very wide variety of ML workflows and workloads. But this batch versus real-time question is a very common one. I'm definitely a big believer in, if you have a scalable, elastic system, you can treat batch and real-time in largely the same way, which has a lot of benefit, because there's often situations where I want to do batch jobs. Maybe I want to run against all the historical data against the model, but I also have live incoming requests and events happening, and I want to classify them or recognize anomalies or whatever the situation might be. So if you can have a system that, you containerize your workload, it can scale up dynamically and manage priority of workloads, so that you can have a batch workload that runs over the course of 5 hours, but it's not overwhelming your scheduler and it's not interrupting your real-time workloads. That can be pretty compelling. But there's other situations where you don't need the real time, and then you might architect the system a little bit differently. But yeah, no, I think that's absolutely one of the key questions to be asking early on when you're designing and asking the question, what does ML look like at my company? Great. Well, and I apologize if I missed any in the chat or anything like that. As I said, I'm more than happy to answer by email or anything else. And look forward to going and attending some of the sessions for the rest of the conference. So thanks, everyone.